Time surrounds every moment of your life, yet it remains untouchable and strangely fragile. You sense it as a steady motion, as a continuous drift that pulls every event forward, whether you welcome it or resist it. From the rhythms of breathing to the turning of the earth, time feels like a river that sweeps all things along its course. But when we step beyond everyday intuition and examine the universe with the sharpest tools of physics, that steady river begins to shimmer. The deeper we look, the more time behaves like an illusion, a convenient story told by the mind rather than a force woven directly into the machinery of nature. Consider the experience of standing under a quiet night sky, far from the noise of cities. Above you, ancient starlight travels across unimaginable distances. You feel the passing of moments because your thoughts form one after another in a sequence. You turn your head, you breathe, you blink. Each action builds the sense that something is flowing. Yet none of these sensations come from time itself. They arise from changes in your body, from electrical signals moving through neurons, from memories that compare past and present. Your brain constructs the idea of flow. Remove the comparison, and what remains is simply the existence of events, not their motion. Physics reinforces this unsettling idea. In the framework of relativity, there is no single universal now that spreads across the cosmos. A distant star can have its own version of the present, and a spacecraft moving quickly relative to you will disagree about which events happen at the same moment. These disagreements are not illusions. They are part of the fabric of spacetime. What feels like a shared instant on Earth might correspond to a different slice of time for an observer racing among the outer planets. There is no privileged clock that dictates the rhythm for all beings in all places. Once this becomes clear, our familiar sense of time begins to feel narrow. We evolved to survive on a world where speeds are modest and gravity is mild. So the stretching and bending of time are not things we feel. Our biology anchors us to a simple present because that is all we need to navigate daily life. Yet the universe is not obliged to respect this simplicity. Space-time forms a four-dimensional arena in which distances and durations shift depending on motion and gravity. Instead of a flowing river, physics presents a tapestry of events laid out together. Motion simply reveals different paths across the tapestry. An even stranger revelation comes from the laws of motion themselves. If you were to reverse every motion in the universe, sending planets backward along their orbits and pushing particles to retrace every collision in perfect reverse, the fundamental laws would cooperate. They allow a universe that runs backward just as easily as one that runs forward. Nothing inside the core equations chooses a direction. Whether things move toward what we call the future or toward what we call the past, the mathematics remains perfectly valid. This symmetry forces an uncomfortable question. If the rules of nature do not prefer a direction, then why do you? Why does every memory sit behind you and every expectation ahead of you? Why does a cup shatter when it falls, but never reassemble itself as it rises? Why do we age in one direction only? Clearly, something in the universe imposes a forward-leaning tendency, but that something is not the classical laws of motion. It must come from a deeper ingredient, one that shapes change in a way that minds later interpret as flow. Some philosophers argue that time is nothing more than change. They propose that events do not happen in time, but instead create time by happening. Others imagine that the entire history of the universe exists at once, like pages of a book already printed, and consciousness simply reads them in order. Physics itself remains neutral. It offers a structure called space-time, but it refuses to say whether time moves. It is entirely silent on the psychological sensation of a present moment. Yet one undeniable fact remains. A cracked glass does not leap back together. Smoke does not return to the match that released it. Warm water does not separate into steaming and freezing halves on its own. The world contains a direction that the laws do not specify, but reality insists upon. Something deep within the universe selects a forward-pointing sense of change. This is the mystery at the heart of our investigation. If time's flow does not originate from the laws of motion and does not arise from relativity's geometry, where does it come from? What hidden principle shapes the arrow we all obey? Before we can answer that, we must explore the one rule of nature that refuses to run backward. It is the only law that breaks the perfect symmetry. It is the rule that never steps in reverse. The broken symmetry reveals itself most clearly in the familiar moments of daily life. You watch a block of ice melt on a warm afternoon, and you immediately understand that it will not spontaneously reform itself. You stir cream into coffee and recognize that the swirling patterns will settle into a uniform mixture, but will never unmix. These small experiences teach a truth far older than scientific theory. They reveal that the universe prefers disorder. It permits complexity to crumble far more easily than it allows complexity to emerge. This tendency is not a psychological illusion. It is a physical law. It is the only major law in nature that has a preferred direction in time. This law is called the increase of entropy, and it is the key to understanding why time seems to move forward. Entropy is a measure of how many microscopic arrangements can produce the same macroscopic situation. A shattered glass can exist in countless configurations of shards scattered across the floor. A whole glass is far more limited in its arrangement. Therefore, the shattered glass represents a higher entropy state. The universe drifts towards states that are easier to achieve simply because they can be realized in vastly more ways. That tendency does not require intention or purpose. It emerges from statistics, from the overwhelming odds that favor disorder. Once you begin to see entropy as a guide for possible futures, you realize that the arrow of time may not be fundamental at all. It may instead be a side effect of initial simplicity evolving into inevitable complexity. But this explanation only deepens the mystery. If entropy increases because disorder is more probable, why was the universe in such an improbably low entropy state in the beginning? Why did existence start from a clean slate instead of a chaotic storm of possibilities? If entropy determines the direction of time, then the birth of time itself must have required an extraordinarily special starting condition. Physicists debate whether this special beginning was spontaneous or whether some principle shaped it. Regardless of the explanation, the fact remains that the visible universe began with remarkable smoothness. Matter was spread evenly, radiation filled space almost uniformly, and the tiny irregularities that existed were so small they could barely disturb the silence. This smoothness is the opposite of what gravity wants. Gravity pulls matter together. It creates clumps, structures, stars, and black holes. If the early universe had been dominated by random chaos, gravity would have behaved differently. Entropy would have been far higher from the start. Time as we know it might not have had a clear direction at all. Instead, something preserved a kind of cosmic innocence. It delivered a beginning of astonishing order. That order created room for entropy to grow. It set the stage for time to unfold with a single direction. It gave rise to the long sequence of events that eventually produced galaxies, stars, planets, and minds capable of questioning the meaning of time itself. When you trace this reasoning to its end, a strange thought appears. Perhaps time does not flow because of something happening in the present. Perhaps time flows because of something that happened at the beginning. The direction we feel might not arise from the present moment at all, but from a boundary condition set long before any observer existed. That boundary, etched into the earliest moments of the cosmos, could be the reason shattered glasses do not reassemble, and the reason you remember yesterday, but not tomorrow. As the universe aged, gravity began shaping matter in ways that increased entropy even further. The earliest wrinkles in the distribution of matter, born from tiny quantum fluctuations, were amplified by gravity into clouds that eventually collapsed into stars. Those stars forged heavier elements, lit the first galaxies, and filled space with energy and motion. All of it unfolded along a direction defined not by the laws, but by the imbalance between the early universe and the future universe. This imbalance remains the engine of change, It is a cosmic gradient, a slope down which every process slides. Without it, nothing would evolve. A universe at maximum entropy would be timeless, not because time disappears, but because nothing would distinguish one moment from the next. Every configuration would look essentially the same. To have time, you must have change. To have change, you must have a gradient. The early universe provided that gradient. Gravity deepened it. You stand today in a cosmos that is still shaped by that ancient asymmetry. The stars you see are the result of entropy increasing. The warmth of your body, the burning of fuel in machines, the weather patterns of the Earth, and even your thoughts rely on energy cascading downhill through that universal gradient. Everything familiar is tied to the same irreversible march. It is the fingerprint of a deeper principle still waiting for final explanation. Yet we are not done searching for the origin of time's arrow. Entropy gives us direction, but entropy itself demands a cause. Why was the beginning so orderly? Why did the universe have room to evolve? The next chapter in our journey investigates this puzzle and the strange idea that the universe was too perfect at its birth. That perfection created imbalance. The imbalance created the arrow, and gravity may be the mechanism that amplified it into everything we see. The perfection of the early universe holds a quiet power over the entire story of time. When astronomers observe the faint afterglow of the Big Bang, the cosmic microwave background, they find a smoothness that borders on astonishing. Temperature differences across vast stretches of sky amount to only a few parts in 100,000. Such uniformity means that matter was arranged with almost no lumps or clumps. Gravity, when presented with such a smooth canvas, has very little structure to work with. Yet this lack of structure is exactly what allowed the arrow of time to emerge. A highly ordered beginning created a vast distance between what the universe was and what it could become. A strange truth appears when we compare gravitational systems with familiar everyday systems. For most forms of matter, a smooth uniform distribution is a high entropy state. Gas filling a room is higher entropy than gas confined in a corner. But gravity behaves differently. For gravity, a smooth distribution represents incredibly low entropy because there are so few possible ways to arrange matter uniformly across space. A clumped distribution, especially one that includes stars collapsing into black holes, has vastly more possible microstates. It carries far higher entropy. In other words, gravity reverses the normal intuition. Smoothness is order, clumpiness is disorder. This insight, first articulated with unusual clarity by the physicist Roger Penrose, reframes the riddle of time's arrow. The early universe was not merely warm and dense, it was astonishingly gravitationally ordered. That order created a universe with room for entropy to grow by unimaginable amounts. The formation of galaxies, the collapse of stars, the formation of black holes, the ignition of nuclear furnaces, and the spreading of heat throughout space all became possible because the cosmos started in a state far from equilibrium. Every step the universe has taken since that beginning has been a slide toward a configuration with greater gravitational entropy. Even now, gravity continues to drive complexity. When a giant cloud of gas collapses under its own weight, gravity squeezes it tighter and tighter. The particles fall inward, gaining speed, colliding and heating. The cloud becomes a star only because entropy increases. The process is irreversible. There is no natural way for a star to uncollapse and return to a cold, diffuse cloud. The direction is fixed. The arrow points the same way for every gravitational process. In this sense, gravity is not just a sculptor of cosmic structure. It is a deep amplifier of the very trend that defines the direction of time. Look at the night sky again. Every star you see is a monument to a one-way journey. It is an engine powered by nuclear reactions that convert mass to energy, spreading heat into space. Those reactions depend on gravitational collapse. They exist because the universe began smooth. They continue because entropy increases. Every galaxy, is a vast collection of such engines. They shine because time has a direction. They exist because gravity magnifies imperfection. The most dramatic examples of gravitational entropy come from black holes. A black hole is not merely a region where light cannot escape. It is an object with an entropy that dwarfs anything else in the cosmos. The entropy of a black hole is proportional to the area of its event horizon, which can be enormous. A single supermassive black hole in the center of a galaxy carries more entropy than all the surrounding stars combined. When matter falls into a black hole, the total entropy of the universe leaps upward. Nothing else produces such a dramatic increase. These extreme objects represent gravity pushed to its ultimate expression. They are the universe's greatest sources of irreversibility. If we imagine the far future of the cosmos, black holes dominate the narrative. Stars will burn out. Galaxies will dim. Matter will cool and drift. Over unimaginably long timescales, black holes will slowly evaporate through quantum processes, releasing faint radiation across the cold expanse of space. Even this evaporation increases entropy. The universe continues its descent toward a final equilibrium, a state in which no further energy gradients exist. In that distant era, time will lose its familiar meaning because every moment will resemble the next. The arrow will fade as entropy approaches its maximum. Yet even this long trajectory traces back to the early universe. The greatest puzzle remains. Why did the cosmos begin in such a low entropy configuration? Why did it start smooth instead of chaotic? Why did gravity have so much room to act? Without that initial condition, there would be no stars, no galaxies, no chemistry, no life, and no perception of time's passage. The arrow of time might not be a fundamental rule. It might instead be a consequence of an improbable beginning. This is where our journey turns toward gravity, not just as a force, but as a potential origin for time's direction. Perhaps gravity did not simply take an ordered beginning and amplify it. Perhaps gravity itself helped define the nature of order at the start. Perhaps the relationship between entropy and spacetime curvature is deeper than we currently believe. The next chapters explore these questions with scientific caution and imaginative precision. We will examine the idea that gravity does more than shape space. It may shape the flow of time. It may be the hidden engine behind the arrow we obey each waking moment. Time seems to move forward because the world around you acts as if it cannot turn back. You watch ice melt, but never unmelt. You watch smoke drift away, but never return to the match that created it. You watch a life unfold step by step, but never retrace itself to an earlier moment. These familiar observations hint at a direction, a sense that the universe prefers one orientation in time over another. Yet this preference is not written into the fundamental rules of motion. It comes from a single principle that stands apart from the others. It comes from entropy. Entropy is often described as disorder, but that word barely touches its meaning. Entropy is a count of how many microscopic arrangements correspond to a given macroscopic state. A neatly stacked deck of cards represents a low entropy state because there are very few ways to arrange it while keeping it neat. Shuffle that deck thoroughly, and the number of possible configurations explodes. The system becomes disordered because almost every random arrangement contributes to the same overall appearance. Nature tends to wander toward these overwhelmingly more probable conditions. That tendency creates the sensation of time flowing from order to disorder. It is not a force pushing events forward. It is a statistical gradient that every process follows. Imagine a drop of ink falling into a glass of water. At the instant it enters, the ink is concentrated, sharply defined, and low in entropy. As the drop diffuses, countless microscopic interactions spread pigment outward. The ink disperses because there are far more ways for the molecules to be mixed than there are for them to remain clumped. If you were to reverse every motion of every molecule, the drop would reassemble, but the laws of nature do not favor that reversal. It is permitted by the equations, yet fantastically unlikely. The universe operates by allowing the most probable future to dominate. The most probable future is almost always one with higher entropy. This statistical truth has a remarkable consequence. It introduces a direction into a universe whose underlying rules have no preference. The increase of entropy becomes the arrow of time. It tells us which states can naturally transform into which others. It restricts the choreography of the cosmos. It explains why you can remember the past but not the future. Memories form when physical systems record information by increasing entropy. The future has not left a mark yet, so there is nothing to recall. The arrow arises from the way reality stores information. Consider the warmth of your hand as you hold a mug of tea. Heat flows from your skin into the cooler ceramic. That flow continues until both temperatures equalize. The equalized state corresponds to higher entropy because energy becomes spread out more evenly. Nothing in the microscopic laws demands that heat must flow from warm to cool. It simply happens because there are many more microscopic arrangements that satisfy that outcome. Once equilibrium is reached, the system cannot spontaneously reverse because that reversal would require an impossibly precise coordination among countless particles. Entropy gives time a direction by making some transformations overwhelmingly more likely than others. The everyday world is filled with such irreversible processes. Burning wood transforms complex structures into simpler ash, gases, and heat. Cracking an egg turns a delicate configuration into a messy mixture that cannot reconstruct itself. Iron rusts, paper yellows, sandcastles crumble under the pull of wind and waves. These irreversible transitions are not flaws in nature. They reveal the statistical shape of reality. Entropy increases because the universe began in a state that allowed it to increase. Without that starting point, time would have no arrow. Yet entropy alone does not tell the whole story. It tells us that the universe evolves from low entropy states to high entropy states because the latter are more probable. But it never explains why the universe began so improbably ordered. It never explains why the early cosmos was smooth enough to provide a foundation upon which the arrow of time could stand. For entropy to climb, the universe must begin in a valley of low entropy. The deeper the valley, the longer the climb. The early universe was a valley carved with astonishing precision. Without that valley, the arrow would fade. To understand the full consequence of this idea, picture the birth of everything. In its earliest moments, the universe was hot and dense, but more importantly, it was smooth. There were no swirling gravitational storms, no tangled webs of matter, no collapsed structures. That smoothness is what made the initial entropy so low. Smoothness may seem like disorder, but gravitationally, it represents extreme order. In a gravitational universe, clumps signify high entropy. Smoothness signifies low entropy. Therefore, the young cosmos stood at the edge of a profound imbalance. That imbalance granted time its direction. As the cosmos expanded and cooled, tiny fluctuations appeared. These small differences in density, seeded by quantum processes, created the first threads of structure. Gravity began amplifying the tiny variations by pulling matter inward into subtle dimples in space-time. Those dimples grew into clouds. The clouds grew into stars and galaxies. Over time, entropy surged. The arrow pointed forward because forward meant moving toward more probable configurations. What makes entropy special is that it is not a straightforward physical force. It is a property of probability. You cannot touch entropy. You cannot isolate it the way you isolate a particle or a field. Yet it governs the unfolding of the universe more profoundly than nearly any other concept. It controls how energy spreads. It limits what patterns survive. It shapes the evolution of matter and radiation. Without it, the universe would be static, a place where past and future are indistinguishable. Thanks to entropy, the universe tells time the direction in which to lean. The rise of entropy explains the direction, but it also prompts a deeper question. If entropy is the statistical engine behind time's arrow, Then what is the origin of its fuel? Why did the cosmos emerge from the Big Bang in such a special low entropy condition that allowed everything to unfold in a single direction? Could gravity itself hold the answer? Gravity behaves in ways that defy ordinary intuition. It turns smoothness into order and clumpiness into disorder. It drives matter to collapse and heat. It transforms potential energy into irreversibility. The possibility emerges that gravity is not simply participating in the rise of entropy, but helping define it. The link between entropy and gravity may hold the key to understanding why the universe chose a forward-moving arrow. In the next step of this exploration, we examine the early cosmos more closely and confront the unusual idea that the universe began too perfect, too smooth, too delicately arranged for the arrow of time to be anything but inevitable. The universe in its earliest moments was astonishingly uniform. Matter filled space almost evenly, with only tiny ripples interrupting the calm. Those ripples were so faint that they represented differences of only a few parts in 100,000. This almost perfect smoothness stands as one of the strangest facts in cosmology because it represents a state of extraordinarily low entropy from the viewpoint of gravity. If entropy measures the number of possible microscopic arrangements, then a universe where matter is scattered into countless clumps has far more possible configurations than one where matter is spread evenly. The gravitational lumps that fill the modern cosmos represent higher entropy states. The early cosmos was the opposite. It was so orderly that it challenges our understanding of how such a beginning could arise. When you imagine the early universe, you might picture a chaotic explosion, but this image is misleading. Instead of chaos, the evidence reveals an uncanny calm. The radiation left over from the Big Bang stretches across the sky with remarkable smoothness. It hints at a beginning not filled with turbulent storms, but with balance and equilibrium. This eerie uniformity is precisely what set the stage for entropy to rise. Without it, the universe would have begun already close to maximum entropy. There would have been little room for change and almost no direction for time to follow. The low entropy beginning is what allowed gravity to amplify small fluctuations into large structures. It provided the necessary asymmetry that made the future different from the past. Entropy can rise only if there is distance to climb. The early universe provided an immense gap between what it was and what it could become. As matter slowly collected under the pull of gravity, entropy increased. Tiny fluctuations grew into clouds. Clouds collapsed into stars. Those stars ignited nuclear fusion, pouring heat into the surrounding space. Galaxies spun themselves apart and reformed. Black holes swallowed matter and increased entropy far beyond the levels reached by ordinary systems. All these events required the early cosmos to be smooth. Smoothness was the improbable seed from which time's arrow sprouted. The smoothness itself demands an explanation. Why did the universe begin this way? One possibility lies in the laws that governed the earliest fractions of a second. During that era, the universe expanded incredibly rapidly, smoothing out irregularities like wrinkles ironed from a sheet. This process, often called cosmic inflation, explains the uniformity of the cosmic microwave background. However, even inflation does not fully answer why the initial conditions allowed such smoothness to occur. The puzzle goes deeper, touching the foundations of physics and the nature of probability in cosmological settings. Whatever the mechanism, the beginning was special enough to distinguish the past from the future. If the early cosmos had begun in a highly clumped configuration, gravity would have behaved differently. Instead of being a creator of complexity, it would have been closer to a stabilizer of disorder. Clumps might have collapsed so rapidly that the universe would have reached equilibrium almost instantly. Black holes would have dominated every corner. Entropy would have been near its maximum from the beginning. In such a universe, the arrow of time would have been weak or non-existent. There would have been no long journey from simplicity to complexity. The future would have looked too similar to the past to define any meaningful direction. Instead, our universe was smooth enough to leave enormous headroom for entropy to grow. That growth created structure. It shaped the cosmic web. It allowed stars to form and burn. It allowed planets to emerge and cool. Eventually, it allowed chemistry to arise. Chemical reactions depend on energy gradients, and those gradients are born from entropy's relentless rise. Life itself is a product of entropy, flowing through matter in organized ways. Without the low entropy beginning, the arrow of time would have been too faint to support the complexity required for awareness. This understanding transforms the question of time's arrow from a question about motion to a question about initial conditions. The direction of time emerges because the universe did not start in a state of equilibrium. It began in a state of spectacular imbalance. That imbalance set everything in motion. It established a preference for one direction over another. If someone were to ask why the universe has a past that looks different from its future, the answer would begin here, in the improbable perfection of the early cosmos. Yet the story does not end with smoothness. Smoothness created possibility, but gravity provided amplification. Gravity is the engine that takes small irregularities and expands them into galaxies. It is the force that shapes the direction in which entropy rises. As the universe evolves, gravity not only magnifies differences, but also creates new pathways for complexity to unfold. It transforms potential into irreversible processes. It deepens the asymmetry that began at the dawn of time. A profound idea begins to surface. Perhaps gravity and entropy are not separate concepts that occasionally interact. Perhaps they are intertwined from the beginning. Perhaps gravity is not only a participant in the arrow of time, but a fundamental contributor to its formation. Whether gravity shapes time or whether entropy shapes gravity remains one of the great debates in modern physics. Before resolving that debate, we must look more carefully at how gravity takes the early perfection of the universe and molds it into the cosmic structures that define our existence. Gravity began its work the moment the universe expanded enough for matter to cool and gather. At first, the differences in density were incredibly small, mere whispers across the cosmic landscape. Yet gravity is exquisitely sensitive to such whispers. Where there was slightly more matter, the pull inward grew slightly stronger. Particles drifted toward these denser regions, increasing their mass and deepening their gravitational wells. As more matter fell inward, the process accelerated. Slight differences grew into significant ones. Over time, the uniformity of the early universe gave way to a rich hierarchy of structures. This transformation marks one of the most important chapters in the story of entropy. When gravity draws matter inward and compresses it, the particles inside the forming cloud collide more frequently. These collisions convert gravitational potential energy into heat. The cloud becomes hotter and denser as it collapses. This heating increases entropy. It is an irreversible process, meaning the cloud cannot spontaneously expand back into a cold, diffuse state without external influences. The collapse illustrates how gravity drives the universe towards states that are, statistically, far more probable. When a collapsing cloud becomes hot enough, nuclear fusion ignites. Fusion is a process in which light atomic nuclei combine to form heavier ones, releasing energy in the process. This release of energy raises the entropy of the surrounding environment. It also allows the star to shine. Every star you see in the night sky exists because a gravitational collapse increased entropy to the point where nuclear reactions became inevitable. The light that reaches your eyes carries information about the irreversible history of its source. Every photon is a messenger that time has advanced. Stars do not merely shine, they sculpt the universe around them. Their radiation shapes nearby clouds, their winds can clear regions of space, and their explosive deaths scatter heavy elements through the cosmos. These heavy elements seed new generations of stars and planets. The entire cosmic cycle of birth and death among stars is made possible by the relentless increase of entropy. Gravity plays the dual role of both creator and destroyer, assembling matter into complex structures and then driving those structures toward their eventual breakdown. The ultimate expression of gravitational collapse is the formation of black holes. A black hole forms when a massive star exhausts its nuclear fuel and collapses beyond the point where light can escape. The resulting object has an entropy that dwarfs every other kind of matter in the universe. The entropy of a black hole is proportional to the area of its event horizon, which means that even a modest black hole possesses an extraordinary number of microscopic states. This makes black holes the most entropic objects known. When matter falls into them, the total entropy of the universe increases dramatically. Black holes reveal a deeper truth about the connection between gravity and entropy. They behave as thermodynamic objects. They have temperature, they radiate energy through a process predicted by quantum field theory, and they possess entropy tied to a geometric property of spacetime. This unexpected bridge between gravity and thermodynamics suggests that these two concepts may share a common origin. The laws governing black holes resemble the laws of ordinary thermodynamics, hinting that gravity might be emerging from more fundamental principles related to information. As gravity continues its work across the cosmos, entropy climbs steadily. Galaxies collide and merge, increasing disorder on enormous scales. Stars burn and die. Gas clouds fragment and reform. Radiation spreads into the cold reaches of intergalactic space. Even the expansion of the universe plays a role. As space grows, energy becomes more diluted and temperatures fall. These changes all contribute to the wider story of cosmic entropy. The direction of time follows this rise. The future is simply the direction in which entropy continues to increase. If we step back and observe this entire process from a cosmic perspective, we see a universe that evolves not because the laws of motion demand it, but because the initial conditions allowed it. Gravity shapes the landscape on which entropy rises. Entropy defines the direction in which complexity flows. The arrow of time emerges from the interplay between these two forces. It is neither purely a property of matter nor purely a property of motion. It is a product of how the universe began and how gravity responded to that beginning. Yet this understanding raises a deeper puzzle. If gravity amplifies entropy and entropy defines the arrow of time, then what created the low entropy beginning that allowed this amplification? How did the early universe achieve its improbable smoothness? Why was the cosmos arranged in a way that permitted change to occur at all? These questions point toward the initial conditions at the birth of spacetime itself. They suggest that the arrow of time may be less a law and more a boundary condition imprinted at the moment of creation. The idea that time's direction arises from boundary conditions, rather than fundamental laws, is both provocative and sobering. It means that the forward march of time is not an inevitable consequence of the universe's structure. It is instead a result of how the universe happened to begin. Change unraveled from order into complexity because the cosmos had the room to do so. The early smoothness was the seed. Gravity watered it. Entropy made it grow into the world we inhabit. These ideas lead to a profound conclusion. The arrow of time is not a feature embedded in the equations, but an emergent property of the universe's history. It is woven into the unfolding of matter and energy across space-time. Understanding its origin means confronting the conditions imposed at the moment of creation. It means examining why the universe chose a state that allowed time to flow instead of stagnate. In the next chapter, we explore this paradox in full. We investigate the notion that the early cosmos was not just smooth, but too perfect, too finely arranged for its gravitational entropy to have been anything but extraordinarily low. This condition set the arrow of time into motion. To grasp why time has direction, we must return to the beginning and examine the remarkable simplicity from which everything emerged. The universe began in a state so smooth and so exquisitely arranged that it stands among the most astonishing facts in all of science. When you look at the cosmic microwave background, the faint afterglow of the Big Bang, you see a portrait of the cosmos as it existed long before stars, planets, or galaxies formed. It is a nearly flawless canvas. The temperature across the sky varies by only a few parts in 100,000. Such precision is not what chaos looks like. It is not what you would expect from a universe born in violent expansion. Instead, it resembles a universe that began in a condition of almost unnatural calm. This calm carries profound implications. For gravity, smoothness is an extraordinarily low entropy state. A universe filled with evenly distributed matter has very few microscopic arrangements compared to one in which matter has clumped into countless structures. Clumped universes are easy to achieve. Smooth universes are not. The early cosmos was therefore special in the extreme. It held an amount of order so immense that the later rise of entropy was not just possible, but inevitable. The arrow of time was seeded in this perfection. To appreciate how unusual this is, imagine a room filled with air molecules. If you released a puff of smoke into the room, the natural outcome would be for the smoke to spread evenly. That spreading corresponds to higher entropy. It is easy to achieve because countless microscopic arrangements produce a mixed state. What is difficult, almost impossibly so, is for the smoke to gather itself back into a compact cloud. The early universe was the reverse of this everyday intuition. It began in the rarest state imaginable, one that could easily have been otherwise. Had matter been irregularly distributed, had gravity inherited a chaotic landscape, the universe would have rushed toward equilibrium far too quickly. There would have been no long period of cosmic evolution, no stable era for stars, and no fertile grounds for life. This puzzle was articulated with striking clarity by the physicist Roger Penrose. He argued that the low gravitational entropy of the early cosmos is the true origin of the arrow of time. His insight reframed the problem. Instead of asking why entropy increases, we must ask why it was so low to begin with. Why did the universe start in a state so carefully arranged that gravity had room to build structure over billions of years? Penrose suggested that the cosmic smoothness represents an unimaginably small fraction of all possible states. The universe began in a configuration so improbable that it forces us to confront the deepest questions about the nature of initial conditions. The wonder of this smoothness becomes even clearer when you consider what gravity eventually did with it. The faint ripples in the early universe grew into galaxies, stars, clusters, and cosmic filaments. These structures represent enormous increases in gravitational entropy. The universe today is wildly clumpy compared to its infancy. That clumpiness reflects the natural tendency of gravity to amplify slight imperfections. Yet none of that growth would have been possible without the early state of remarkable order that allowed entropy to rise so dramatically. This raises a question that lies at the edge of cosmology. How did the universe achieve such perfection at its birth? One possible answer comes from the theory of cosmic inflation. According to this idea, the universe expanded at a staggering rate during its earliest fraction of a second. This rapid expansion stretched space so quickly that any irregularities were smoothed out. Inflation acts like a cosmic ironing process, erasing wrinkles and leaving a uniform field behind. It also magnifies tiny quantum fluctuations so that they later seed the large-scale structure of the cosmos. Inflation, however, may not be the final explanation. Even if inflation smoothed the universe, it still requires an initial state capable of triggering the inflationary expansion. Some physicists argue that the true question lies not in inflation itself, but in the deeper laws governing the birth of spacetime. Others propose that the universe may have emerged from a quantum process in which smoothness was favored. Whatever the answer may be, the universe did not spring from chaos. It emerged from a beginning so delicately balanced that its entropy could only rise from that moment onward. The perfection of the early cosmos is what made the future possible. It created room for gravity to sculpt galaxies. It allowed stars to ignite and endure. It permitted long periods of stability in which complexity could unfold. Without that perfection, the universe might have burned out quickly or collapsed in upon itself. There would have been no chemistry, no biology, no thought. The arrow of time would have been faint or non-existent. The world you inhabit could never have formed. We now face an extraordinary idea. Perhaps the arrow of time does not arise from the laws of nature acting in the present, but from the condition imposed at the very beginning of the universe. Perhaps time points forward, because the universe began in a state unlike anything else it will ever experience again. The earliest moment was a boundary condition that set the direction for everything that followed. Gravity carried out the instructions contained in that initial smoothness. Entropy increased as gravity collapsed clouds, formed stars, and built the cosmic web. The arrow is the unfolding of that original imbalance. This brings us to a crucial transition. The early universe was smooth and low in entropy, but gravity turned that smoothness into complexity. Gravity is not simply a passive observer of cosmic change. It is an active driver of entropy. It takes small differences and amplifies them. It deepens the gradient that propels time forward. It transforms the perfection of the early cosmos into the rich and dynamic universe we see today. To understand how gravity became the engine of cosmic complexity, we now move deeper into the role it plays in shaping matter, energy, and entropy on the grandest scales. If the early universe gave time its direction, gravity ensured that direction would become visible, powerful, and irreversible. Gravity entered the young universe as both a sculptor and an instigator. From the moment matter cooled enough to drift rather than collide violently, gravity began to influence the cosmic landscape. What had once been a nearly flawless sea of evenly spread particles now carried faint ripples. These ripples, tiny variations in density left behind by quantum fluctuations, were the seeds upon which gravity would act. In a perfectly uniform universe, gravity would have had nothing to pull upon. With no differences to amplify, no regions slightly denser than others, the cosmos would have remained smooth forever. But the faint imperfections were enough. They allowed gravity to begin its long task of shaping structure. As matter began to gather, a profound transformation occurred. The gravitational collapse of a gas cloud does not simply rearrange matter. It converts potential energy into heat. Particles falling inward accelerate, collide, and generate internal motion. This motion increases the entropy of the cloud. What started as a delicate gravitational dip becomes a hot, swirling region with countless microscopic configurations. This increase in entropy marks an irreversible step in the story of cosmic evolution. A cloud that has collapsed and heated cannot spontaneously revert to its original cold and diffuse state. Gravity sets into motion processes that cannot run backward because the number of possible outcomes is too large and too disordered for nature to reconstruct. Eventually, the center of a collapsing cloud grows hot enough to ignite nuclear fusion. This is the moment a star is born. Fusion transforms hydrogen into heavier elements and releases immense amounts of energy. The heat radiates outward into space, increasing the entropy of the surrounding environment. The star itself maintains its structure by balancing the inward pull of gravity with the outward push of radiation. Over millions or billions of years, the star acts as an entropy generator, steadily converting nuclear fuel into heat and light that streams across space. Every star you see is both a beacon of energy and a testament to the rise of entropy. It burns only because gravity prepared the conditions necessary for fusion to occur. As stars live and die, they enrich the universe with heavy elements. Massive stars explode as supernovae, scattering carbon, oxygen, iron, and countless other atoms into interstellar space. These elements become the building blocks of planets and eventually of life. Supernovae are among the most powerful entropy-increasing events in the cosmos. They transform highly ordered stellar cores, into expanding clouds of hot gas with unimaginable complexity. Once again, gravity is at the heart of the process. It enables the formation of stars, guides their evolution, and triggers their explosive ends. But the most extreme consequences of gravitational collapse occur when a massive star reaches the end of its life and cannot support itself against its own weight. The collapse deepens until the star forms a black hole. These objects represent the highest entropy per unit of mass known to physics. Their entropy is so colossal that it dwarfs the sum of all the ordinary matter in a galaxy. The formation of a black hole is not simply another step in cosmic evolution. It is a dramatic leap in entropy. When matter crosses the event horizon, the information about its precise configuration becomes hidden from the outside universe. The entropy increases because the number of internal microstates compatible with the black hole's external properties is vast. A black hole is the ultimate expression of gravitational disorder. This interplay between gravitational collapse and entropy is central to our understanding of time's arrow. Each collapse increases entropy. Each formation of a star or a black hole contributes to the asymmetry between past and future. The early universe was smooth and low in entropy. Gravity took that simplicity and turned it into complexity. Because of this, the universe developed a direction. It moved away from the improbable perfection of its beginning and toward a future filled with increasingly disordered structures. Time's arrow becomes visible in the collapse of clouds, the fusion of atoms, the explosion of stars, and the quiet formation of black holes. Even processes that seem gentle can reveal the gravitational influence on entropy. When galaxies collide, their shapes distort and their stars orbit in new chaotic paths. Gas is funneled towards central regions, triggering new star formation. Black holes may grow as they consume matter stirred by the collision. The aftermath of such an event carries far higher entropy than the original arrangement. Gravity drives these transformations because it magnifies small perturbations into large-scale structures. In doing so, it deepens the entropy gradient that the universe follows. This deepening of the entropy gradient holds a subtle implication. It means that gravity does not merely lead the flow of time, it participates in defining it, by determining which states are more probable and by enabling the formation of high entropy objects like black holes. Gravity shapes the landscape along which entropy increases. In a sense, gravity writes the script that entropy follows. Without gravity, the rise of entropy would be far slower and far less dramatic. Time would have a weaker arrow, perhaps too weak to support complex structures or life. The natural question that follows is whether this relationship runs in one direction or two. Does gravity shape entropy, or does entropy shape gravity? Some theories suggest that the connection between them is not accidental, but fundamental. They propose that the structure of spacetime itself may arise from thermodynamic principles. If true, then the arrow of time would not merely depend on gravity, but might be built into the very geometry of the universe. Such ideas challenge our intuition and require careful skepticism, yet they offer a path toward understanding how time, entropy, and gravity might share a common origin. Before diving into these deeper theoretical waters, we must complete our picture of gravity's role in creating cosmic complexity. The rise of entropy through gravitational collapse does not merely explain why stars shine or black holes form. It explains why time can be experienced at all. Without the gradient created by the early universe and amplified by gravity, the cosmos would lack the contrast needed to separate past from future. The arrow of time is written into the distribution of matter, the temperature of space, and the dynamics of gravitational collapse. Everything we have observed so far points toward gravity as the engine that drives the universe from its smooth beginning into its chaotic and intricate present. To understand why this engine works so effectively and why its influence is universal, we now turn to the question that stands at the journey's midpoint. If the early universe was too perfect for its own good, then gravity was the force that released that perfection into motion. It is time to examine more closely how gravity transforms low entropy smoothness into high entropy structure, and whether this transformation is the very thing that defines the flow of time. Gravity's ability to turn perfection into complexity is not only a story of collapsing clouds and exploding stars. It is a story of how the universe found its direction. To grasp this fully, imagine once again the early cosmos as a smooth and nearly featureless expanse. In that perfection, there was almost no distinction between one region and another. There were no structures to evolve, no gradients to follow, and no meaningful difference between earlier and later moments. Time, as we recognize it, would have had no texture in such a world. A universe in perfect equilibrium is a universe without history. For history to exist, that equilibrium had to be disturbed. Gravity was the agent of that disturbance. By amplifying microscopic fluctuations, gravity created paths along which entropy could increase. These paths gave rise to all forms of complexity, from the formation of stars to the distribution of galaxies across billions of light years. The structures that emerged were not simple arrangements. They were intricate and dynamic. They interacted, fragmented, merged, and evolved. Each transformation pushed the universe further from the low entropy smoothness of its beginning. Each transformation made time feel more directional. The universe became richer because gravity deepened the gradient along which entropy could climb. Consider the cosmic web, an immense network of filaments and clusters that spans the visible universe. These filaments were drawn out over billions of years by gravity pulling matter into threads and nodes. The web demonstrates the cumulative effect of gravitational amplification. Where matter was slightly denser, gravity pulled more matter. Where gravity pulled more matter, entropy increased as heat and motion built within collapsing regions. Each collapse created new opportunities for complexity. Stars formed within dense pockets. Groups of stars became galaxies. Galaxies gathered into clusters, then into superclusters. The cosmic web is the grand architecture of rising entropy. Within this architecture, the flow of energy is essential. Stars convert nuclear potential into radiation. Black holes convert mass into Hawking radiation over unimaginable timescales. Supernovae release tremendous bursts of energy. Gas clouds heat and cool as they form new stars. Every transfer and transformation contributes to entropy. Every exchange of energy reinforces the arrow of time because it spreads energy from concentrated forms into diffuse ones. The flow of energy, shaped entirely by gravitational evolution, is the means through which the universe records its irreversible history. You can feel this history directly in the warmth of the cosmic microwave background. That faint radiation is the relic of a time when the universe was young. It has cooled from thousands of degrees to just a few degrees above absolute zero. Its photons have stretched as space expanded, losing energy along the way. Every photon in this ancient glow is a reminder that entropy has been rising since the cosmos began. Gravity ensured that the radiation would thin and cool, while matter clumped into higher entropy structures. Without gravity, this separation of fates would not have occurred. Matter and radiation would have remained in a uniform sea, lacking any direction for change. What makes this entire story remarkable is how naturally gravity creates order out of smoothness, while simultaneously increasing disorder overall. When a cloud of gas collapses, gravity produces a star that seems more ordered than the original cloud. A star is a distinct object with clear boundaries and internal structure. Yet from a thermodynamic perspective, the entropy increases because the collapse generated heat and released energy into the surrounding space. The star looks orderly, but contributes to disorder. This duality lies at the heart of why gravity is so effective at driving the arrow of time. It creates complexity through processes that are fundamentally irreversible. Even after billions of years, the universe remains in a transitional state. It has not reached maximum entropy, Galaxies continue to merge, stars continue to burn, black holes continue to grow, entropy continues to rise. The cosmos is not yet old enough for equilibrium. It is still young compared to the timescales required for black holes to evaporate and for matter to spread into thin cosmic haze. The arrow of time remains strong because there is still room for entropy to climb. The universe still has a deep well of gravitational potential energy left to explore. Eventually, far in the future, the cosmos will approach a state where entropy nears its maximum. Stars will fade, black holes will evaporate, matter will disperse, energy will spread nearly uniformly across space. In that distant epoch, the arrow of time may lose its meaning because changes will become minimal. When every region of space looks nearly identical to every other region, the distinction between past and future blurs. Time becomes directionless, not because it ceases to exist, but because nothing in the universe responds to it. The arrow requires imbalance. Once imbalance disappears, the arrow dissolves. This projection into the future reinforces the idea that time's direction is tied to the history of entropy. It is not imposed by the laws of motion. It is a condition of the universe's evolution. It arises from the initial perfection that gravity unraveled. It is a product of the cosmic gradient that still drives change today. This realization brings us to a delicate turning point in our exploration. If the early universe was too perfect, and if gravity transformed that perfection into the complexity we see now, then what exactly is the relationship between gravity and entropy? Is gravity merely responding to the low entropy beginning, or is gravity itself fundamentally linked to the very notion of entropy? Some modern theories suggest that the fabric of space-time and the force of gravity may arise from thermodynamic principles. If that is true, then the arrow of time may be etched into the geometry of the universe at its most foundational level. Before we explore these bold ideas, we must complete Chapter 3 by acknowledging the central paradox. The early universe was unimaginably smooth, yet that smoothness is what allowed the universe to evolve into something rich and varied. It was too perfect for its own good, and through that perfection, time found its direction. Gravity shaped the universe with a slow and unyielding patience, taking the nearly perfect smoothness of the early cosmos and bending it into the intricate structures we see today. In its earliest form, the universe did not possess galaxies, stars, or anything resembling the complexity that fills the night sky now. It carried only the faintest hints of irregularity, tiny variations in density that drifted like whispers through a vast and glowing fog. Yet these small imperfections were enough. Gravity seized them, amplified them, and used them as blueprints for the architecture of the cosmos. From this simple beginning, it created beauty, violence, order, and chaos, all intertwined in the cosmic web that stretches across billions of light years. To appreciate how gravity becomes the engine of complexity, imagine a large cloud of gas floating in the darkness of space. In the absence of gravity, that cloud would remain as it is, cold and diffuse, spreading gently as particles drift. But under the influence of gravity, every particle pulls upon every other particle. Where there is slightly more mass, the pull inward becomes slightly stronger. A small advantage grows with time. Matter drifts toward the denser region. The drift makes the region denser still. Gravity does not simply gather matter, it accelerates the gathering. What begins as a whisper of imbalance becomes a pronounced collapse. This collapse transforms the simple cloud into a place of turbulence and heat. As particles fall inward, they gain speed, collide, and transfer energy. These collisions turn gravitational potential into internal motion, causing the temperature to rise. The heating increases entropy, and this increase is irreversible. A hot, dense cloud cannot spontaneously revert to its earlier cold and uniform state. There are far more ways for the particles to arrange themselves in a heated, turbulent configuration than in a cool, quiet one. Gravity has already begun the irreversible march up the entropy gradient. As the collapse continues, the center of the cloud becomes so hot and so densely packed that nuclear fusion ignites. In that moment, a star is born. From the outside, a star appears serene, a steady point of light burning across unimaginable distance. Inside, it is a furnace, a churning ocean of plasma where hydrogen nuclei slam together to form helium, releasing tremendous amounts of energy. This energy travels outward, radiating into space as light and heat. Every photon is a fragment of disorder. Every ray of light is a delivery of entropy into the surrounding universe. The star is a machine that converts gravitational collapse into thermodynamic irreversibility. The birth of a star marks only the beginning of gravity's creative cycle. Stars forge heavier elements in their cores. They cast powerful winds across nearby space. They influence gas clouds, triggering new rounds of collapse and new generations of stars. In doing so, they weave complexity from the interplay of matter and light. All of this arises because gravity deepened the simple imperfections present in the early cosmos and created the conditions under which fusion could ignite. Stars do not live forever. Their lifetimes depend on their mass. Small stars burn slowly, providing steady heat over tens of trillions of years. Massive stars burn fiercely, exhausting their fuel in only a few million years. When a massive star dies, gravity once again asserts its dominance. The outward push of radiation weakens as the fuel depletes. Gravity overwhelms the internal pressure and forces the star to collapse. The collapsing core rebounds violently in a supernova explosion, releasing more energy in a few moments than a typical star emits over its entire life. The explosion seeds space with heavy elements, the raw material for planets and living chemistry. It also increases entropy in dramatic ways, spreading energy across space in a chaotic and irreversible rush. Sometimes the collapse is so extreme that it produces a black hole, the most entropic individual object known. Black holes have entropy proportional to the area of their event horizons, and this entropy is enormous. A black hole of stellar mass carries far more entropy than the star that formed it. A supermassive black hole at the center of a galaxy carries more entropy than the billions of stars orbiting around it. When matter crosses the event horizon, the universe's entropy jumps. No other process is as efficient at expanding the realm of possible microscopic configurations. A black hole is gravity's ultimate instrument of disorder. Yet gravity does not merely destroy, it builds and refines. Galaxies collide and merge under its influence. Their stars weave through each other like schools of fish passing in the dark, rarely colliding but always responding to the gravitational tides. Gas clouds are compressed by these cosmic encounters, triggering new rounds of star formation. Central black holes grow by swallowing matter stirred by the collision. The final galaxy shines more brightly and exists in a more entropic state than either of the galaxies that entered the merger. Through these interactions, gravity sculpts the large-scale structure of the universe while continually driving entropy higher. Across cosmic distances, the universe forms a vast web of filaments and voids. The filaments contain galaxies and clusters bound by gravity, while the voids are enormous regions nearly empty of matter. This pattern arose from the delicate initial fluctuations left behind by the early cosmos. Gravity, acting like a cosmic artist, stretched these faint contours into sweeping arcs of structure. The web reveals how gravity magnifies small differences into great ones. Its existence is a testament to the profound relationship between structure formation and entropy growth. Although gravity creates order in the sense that it forms stars and galaxies, it also ensures that these structures participate in the rise of disorder. A galaxy filled with stars may appear organized, yet the processes that formed it increased entropy on colossal scales. Every collapsed cloud, every fusion reaction, every stellar death, and every black hole formation contributes to the arrow of time. The universe is able to evolve because it began in a low entropy state and because gravity provides a mechanism to move away from that beginning. One of the most intriguing realizations in modern physics is that black holes suggest a deep link between gravity and thermodynamics. The fact that black holes have temperature and entropy and radiate energy over time hints that gravity might emerge from statistical behavior at a more fundamental level. If gravity is connected to entropy in this way, then the growth of complexity and the direction of time may be intrinsic to the very geometry of spacetime. The arrow of time might not simply be a result of low entropy initial conditions. It might be built into the relationship between gravity and information. This possibility invites a new question. If gravity shapes the universe in ways that always increase entropy, does gravity actively create the arrow of time? Or is gravity itself a response to the universe's need to increase entropy? The universe may be telling us that the same principle guiding thermodynamics also guides geometry. The rise of entropy may not be something that happens within spacetime. It may be something that creates spacetime. This chapter leaves us standing at the edge of this profound concept. Gravity has shown itself to be the engine of complexity, the driver of entropy, and the amplifier of the early universe's perfection. To understand whether gravity also creates time's direction, we must now dive deeper into scenarios where gravitational processes themselves become tangled with the nature of time. We must explore how time behaves in the strong gravity of collapsed stars and near the event horizons of black holes. We must examine whether gravity merely shapes the arrow or whether it defines the stage upon which the arrow exists. Gravity has always appeared as a force that simply pulls matter together. Yet when we follow its influence across the history of the cosmos, a deeper pattern emerges. Gravity does not merely arrange matter. It creates irreversible events. It transforms smoothness into structure and structure into collapse. It turns potential into heat and heat into radiation that spills outward into the darkness. Each of these transformations increases entropy. Each of them pushes the universe further from its original simplicity. When viewed in this light, gravity begins to resemble not just a sculptor of matter, but a guide for time itself, a principle that ensures the future differs from the past. To understand this possibility, fully imagine again a cloud of gas drifting silently in the emptiness of space. If nothing acted upon it, the cloud would continue drifting forever, gradually spreading and cooling, but never collapsing into complexity. Gravity changes that fate. Its pull draws particles inward, triggering collisions that heat the cloud. The heat flows outward, and the cloud cannot reverse its path. With that first irreversible step, the arrow of time begins to sharpen. The collapse leads to fusion, which leads to energy release, which leads to chemical enrichment, which leads to planets, and all the intricate processes that follow. Each stage depends on gravity converting gravitational potential into forms of motion and heat that cannot be undone. Each stage ties the future to the irreversible consumption of available energy. This suggests that gravity might be more than a bystander in the growth of entropy. It might be the very mechanism that turns potential gradients into irreversible evolution. When matter collapses, gravity provides the means by which energy is released in a form that spreads into the environment. When matter forms a star, gravity sets the conditions under which the star burns. When the star dies, gravity dictates whether the remnant becomes a white dwarf, a neutron star, or a black hole. At every step, gravity acts as a converter of order into complexity, and complexity into irreversibility. If time requires a direction, then gravity provides the mechanism that ensures that direction is obeyed. One of the strongest arguments that gravity creates the arrow of time arises from the simple fact that gravitational collapse is inherently asymmetric. A cloud can collapse into a star, but a star cannot spontaneously decohere into a cold, diffuse gas cloud. A galaxy can merge with another galaxy, but a merged galaxy cannot separate into its original components without external intervention. A black hole can form from collapsing matter, but the reverse process, where a black hole ejects matter in a way that restores the original star, is not permitted by known laws of physics. These asymmetries are signatures of the arrow of time. They reveal that while the underlying equations may be time-symmetric, the presence of gravity ensures that only one direction is physically realized. But why does gravity behave in this directional way if the equations of physics themselves contain no orientation in time? One answer lies in the initial conditions of the universe. The early cosmos was smooth and low in entropy. Gravity had almost no structure to work with. In such a state, the only possible direction for the universe to evolve was toward increasing complexity. Gravity did not create the arrow ex nihilo. It magnified the arrow that was already encoded in the beginning. The seed of direction existed in the initial smoothness. Gravity watered that seed by amplifying imperfections and guiding matter into states of higher entropy. The arrow of time emerged because the universe began in a condition that had only one likely path. This explanation seems satisfying, yet it leaves open a deeper question. If gravity amplifies the arrow of time, does it also depend on entropy to exist in the first place? Some researchers have suggested that gravity may not be a fundamental force at all, but an emergent phenomenon arising from statistical behavior in underlying microscopic degrees of freedom. In this view, spacetime itself might arise from the way information and entropy are organized. If this is true, then gravity would not merely create entropy. Entropy would also create gravity. The two concepts would be inseparable, two sides of a deeper principle that determines both the geometry of spacetime and the direction of time. Consider a star collapsing to form a black hole. The event horizon that emerges is a surface that hides all information about the interior from an outside observer. The entropy of the black hole, tied to the area of this surface, suggests that the geometry itself encodes a form of statistical behavior. The fact that black holes radiate energy, slowly losing mass over time, reinforces the idea that gravity and thermodynamics share a common foundation. The irreversible evaporation of a black hole is another expression of the arrow of time, yet it is dictated entirely by the curvature of spacetime around the hole. This connection between geometry and irreversibility hints that gravity might indeed help create the arrow. On the other hand, if gravity is emergent from entropy, then the direction of time emerges first. The arrow of time would be a property of how microscopic information is arranged. The curvature of spacetime would arise from this informational structure. Gravity would act as the macroscopic manifestation of an underlying thermodynamic law. In this scenario, time's direction causes gravity rather than the reverse. The two concepts become inseparable because they are born from the same informational foundation. Both interpretations push physics toward its limits. They challenge the assumption that space and time are fundamental. They force us to imagine that the universe might be built from something deeper, perhaps patterns of entanglement or degrees of freedom that are not spatial in any conventional sense. What matters for our journey is that these ideas strengthen the connection between gravity and the arrow of time. Whether gravity creates the arrow or whether the arrow gives rise to gravity, the two appear intertwined. Neither concept seems to make full sense without the other. This entanglement of ideas encourages a new way of viewing time's direction. Instead of thinking of time as a river that flows, we can think of it as the unfolding of the universe's initial conditions under the guidance of gravity. Time moves forward because the universe is moving from a low entropy state to a higher one. It moves forward because gravity makes it virtually impossible for matter to evolve in any direction except the one that increases entropy. The arrow of time is the visible trace left behind by the fact that gravity harnesses imperfection and turns it into structure. In this sense, gravity acts as the engine that converts the early smoothness into the future's complexity. Without gravity, the universe would have remained nearly uniform, a featureless sea with no stars, no galaxies, no planets, and no observers. Time would have been a shallow concept because nothing would have changed in meaningful ways. With gravity, the universe gained a mechanism to generate depth, evolution, and irreversibility. Gravity is the translation of potential into history. Yet even with this understanding, our search is not complete. We have followed gravity's role in shaping the arrow of time across cosmic evolution, but we have not yet examined how gravity influences the experience of time itself. Time does not pass at the same rate everywhere. Near massive objects, clocks tick more slowly. In extreme gravitational fields, the notion of time begins to bend, twist, and slow almost to stillness. If gravity amplifies the arrow of time by increasing entropy, it might also shape the very flow of time through space-time geometry. To understand whether the arrow of time is global or local, directional or contextual, we must step into the strange territory where gravity becomes strong and time begins to behave in unfamiliar ways. Time has always felt like the most universal ingredient in existence, a steady rhythm that ticks the same everywhere in the cosmos. You imagine distant galaxies aging alongside the Earth, their stars shining through the same passage of moments that measure your own life. Yet the universe does not grant such equality. Time is not a single beat. It is a fabric that stretches and squeezes depending on where you stand. Gravity, the same force that pulls your feet to the ground and guides planets through their orbits, also alters the flow of time itself. It shapes the pace of moments, slows the passage of seconds, and bends the unfolding of events. When you move through regions of different gravitational strength, you are not simply changing your position. You are stepping into different tempos of existence. Imagine standing on the surface of the Earth, feeling the familiar downward pull beneath your feet. According to general relativity, this pull is not a force in the traditional sense, but a sign that space-time is curved. The mass of the Earth warps the geometry around it, creating a landscape through which objects move. What Einstein discovered is that this curvature influences not only the path of objects, but the passage of time. A clock resting beside you on the ground ticks slightly slower than a clock far above the planet where gravity is weaker. This difference is incredibly small, yet it is measurable. It affects the operation of satellites, navigation systems, and all technologies that rely on precise timekeeping. Without correcting for this gravitational slowing, global positioning systems would drift by kilometers in a single day. The flow of time is intertwined with the fabric of space-time, and gravity is the sculptor of that fabric. Now imagine climbing a tall mountain. At the summit, gravity is ever so slightly weaker than at the base. You would not notice any difference in your breathing or your heartbeat, but a clock strapped to your wrist would tick a little faster than it would at sea level. The higher you go, the faster time passes. It does not rush, it does not leap, but it glides more quickly, a subtle shift that only precise instruments can detect. This difference reveals a deeper truth. Time is not uniform. It is influenced by mass, energy, and motion. The universe does not provide a single universal moment. Instead, it delivers countless local moments, each shaped by its surroundings. When we leave the gentle gravitational field of the Earth and journey toward more extreme environments, the distortion of time becomes profound. Picture a neutron star, the collapsed core of a once massive star. It contains more mass than the Sun packed into a sphere only a few kilometers wide. The gravity at its surface is so intense that an observer hovering just above it would experience time at a dramatically slower pace than someone far away in open space. A single second near the neutron star might correspond to many seconds for a distant observer. If you could stand safely on the surface of such a star, which is impossible given its conditions, you would find that the cosmos above you races ahead while your own moments unfold slowly. The distortion is not an illusion. It is the natural behavior of space-time when pushed into extreme curvature. The effect becomes even more dramatic near a black hole. A black hole is not merely a region of strong gravity. It is a place where space-time is curved so intensely that all paths lead inward. Surrounding the black hole is the event horizon, a boundary beyond which nothing can escape. For an observer watching from afar, an object falling toward a black hole appears to slow as it approaches the horizon. Light emitted from the falling object stretches into longer and redder wavelengths. The clock carried by the object ticks more slowly. The approach to the event horizon seems to take forever. From the distant observer's perspective, time for the falling object nearly stops at the boundary. Yet for the person falling, time feels normal. Their heartbeat continues, their thoughts flow, their clock ticks at its usual pace. They do not feel any sudden halt as they cross the event horizon. Once inside, they move toward the center in a finite amount of time. The contradiction between their experience and the distant observer's view is not a paradox. It reveals a truth about space-time. Time is subjective, dependent on the path one takes and the curvature through which one travels. Each observer carries their own slice of space-time. Their experiences do not need to align. They coexist within the geometry of the universe, each correct in their own frame. This peculiar behavior forces us to rethink our assumptions about the arrow of time. If time flows differently in different regions, does the arrow itself change direction or intensity? Does gravity alter not only the rate of time, but its forward orientation? The answer begins with acknowledging that the arrow of time is tied to entropy. It is not simply a feature of the ticking of clocks. Entropy increases regardless of how quickly or slowly clocks run. A process that is irreversible in a weak gravitational field remains irreversible in a strong one. If a star collapses into a black hole, the entropy increases dramatically. That increase does not reverse merely because time dilation stretches the external perception of the event. Whether time appears slow or fast to an observer, the march toward higher entropy persists. This means the arrow of time remains intact even in the most extreme environments. Close to a black hole, time slows for the object falling in, yet the entropy of the universe still increases. The black hole grows as it absorbs matter. Its entropy, tied to the area of its event horizon, increases significantly. Even though the outside observer perceives the infalling object as frozen at the brink of the horizon, the entropy associated with the black hole rises in a way that is irreversible. Gravity's distortion of time does not erase the arrow. It reinforces it through the rise of entropy that accompanies collapse. This relationship between gravitational time dilation and entropy suggests that gravitational environments carry their own thermodynamic signatures. A region of strong gravity is not simply a place where time runs slowly. It is a place where the geometry of space-time encodes information in particular ways. The event horizon of a black hole, for example, is closely linked to entropy. The idea that the entropy of a black hole is proportional to the area of its horizon reveals that geometric properties hold thermodynamic meaning. This connection between entropy and geometry hints that gravity may be more than a force. It may be a manifestation of underlying informational dynamics. Consider the evaporation of a black hole through Hawking radiation. Over unimaginably long timescales, black holes emit radiation due to quantum effects near the horizon. This radiation carries away energy and information, causing the black hole to shrink slowly. The process is incredibly slow, especially for large black holes, but it is irreversible. It increases the entropy of the surrounding environment, even as the black hole itself loses mass. This evaporation shows that black holes are not static, empty pits. They are thermodynamic systems that follow laws resembling those of heat and energy. They convert curvature into radiation and radiation into entropy. The arrow of time permeates even this exotic process. If gravity and entropy are so deeply connected, then a new picture of time begins to emerge. Time may not simply run through a pre-existing landscape. It may be shaped by the geometry of space-time, which in turn may be influenced by entropy and information. Regions of strong gravity slow time not simply because of mass, but because the geometry requires it. Entropy rises in these regions in ways that encode information on surfaces like event horizons. This suggests that time, gravity, and entropy form a triad of interconnected ideas. Each shapes the others. Imagine a traveler falling into a black hole. experiencing seconds while the universe outside ages by years or centuries. For the traveler, time is normal. For the outside observer, it is nearly frozen. Both viewpoints are correct. What links them is entropy. The traveler's fall is irreversible. The black hole gains mass and entropy. The universe outside cannot reverse the process, even if it perceives the fall as stretched across enormous spans of its own time. The arrow of time points in the same direction for both observers, even though their clocks disagree. It is entropy, not the rate of time itself, that defines the arrow. This realization deepens the mystery. If the arrow of time persists even in the most distorted regions of space-time, then the origin of the arrow must lie deeper than the flow of time itself. It lies in the initial conditions of the universe and the ways gravity amplifies those conditions. Time runs slower in strong gravity, yet the direction in which it points remains unchanged. The flow may stretch or compress, but the gradient of entropy does not reverse. Gravity shapes the pace of time, but not its orientation. From these ideas emerges a profound question. If gravity alters time's rate and entropy defines time's arrow, could the two be aspects of a deeper principle? Could the curvature of space-time arise from informational or thermodynamic rules? Could the arrow of time be etched into the geometry of the universe because geometry itself emerges from entropy? These questions lead us toward theories that view gravity not as a fundamental force, but as an emergent phenomenon, born from the statistical behavior of microscopic degrees of freedom. The next chapter explores this frontier directly. It will take us into ideas where space-time arises from information, where gravity emerges from entropy gradients, and where the arrow of time is not imposed on geometry, but born from it. To continue our journey, we must step beyond the familiar world of curved space-time and enter a realm where geometry, entropy, and time become intertwined expressions of the same underlying reality. Gravity has always been treated as one of the fundamental forces of nature, a cornerstone in the architecture of physical law. Yet in recent decades, a remarkable idea has taken shape, suggesting that gravity might not be fundamental at all. It might instead be an emergent phenomenon, a large-scale behavior arising from the microscopic structure of space-time. In this view, gravity is to space-time what pressure is to a gas or what temperature is to a room. It is not a fundamental ingredient, but a collective behavior that emerges when countless degrees of freedom interact. If this is true, then time itself and the arrow that guides it may have roots not in geometry alone, but in the thermodynamics of information. Imagine a vast ocean. From a distance, you see waves rolling across its surface. They are graceful and continuous, like smooth ripples moving across a fluid sheet. Yet the waves are not fundamental. They are not made of some new substance. They arise from the collective motion of trillions upon trillions of water molecules. You cannot point to a single molecule and say it contains the wave. The wave is a large-scale pattern. It is real, but it emerges from the interactions of a deeper microscopic system. Many researchers now believe gravity might be similar to that wave. It is real, powerful, and essential, but it may be an emergent feature of something more fundamental. This idea gained momentum when physicists began exploring black hole thermodynamics. A black hole has entropy and temperature. It radiates energy extremely slowly through quantum effects near its horizon. The entropy of a black hole is proportional to the area of its horizon rather than its volume, which is unusual. In every familiar physical system, entropy scales with volume because entropy counts the number of possible internal arrangements. The fact that a black hole's entropy scales with area hints at a surprising conclusion. It suggests that the information describing everything inside might somehow reside on the surface. This idea resembles a hologram, where a two-dimensional surface codes for a three-dimensional picture. It led to the notion that space-time itself might be holographic in nature, storing its fundamental information on surfaces rather than volumes. This strange possibility touched the work of Jacob Bekenstein and Stephen Hawking, who recognized that black holes behave like thermodynamic systems. Later, Ted Jacobson made a bold connection. He demonstrated that Einstein's equations for gravity could be derived from the basic laws of thermodynamics applied to patches of spacetime. In other words, gravity may be nothing more than a thermodynamic equation of state for spacetime. It may arise from deeper microscopic principles, the same way the laws of fluid dynamics arise from underlying molecules. If this is true, then the arrow of time may be woven into gravity because gravity is woven into entropy. Entropy always increases in closed systems. The direction in which entropy rises defines the arrow of time. If gravity itself emerges from entropy gradients, then the arrow of time might not merely accompany gravity, it might create gravity. One of the boldest articulations of this idea came from Eric Verlinde. He proposed that gravity may be an entropic force, a phenomenon that appears whenever a system seeks to increase its entropy. In his view, objects move toward one another not because of a fundamental force, but because the universe tries to maximize its entropy. A mass placed in spacetime disturbs the informational structure. Other masses move in ways that restore the balance by increasing entropy. The motion we call gravitational attraction may simply be the unfolding of this information-seeking process. Imagine holding an object near the horizon of a black hole. As you lower the object toward the edge, the entropy of the horizon increases. The increase arises not from the motion of matter, but from information about the object being encoded on the surface. Verlinde argued that ordinary gravity might work in a similar way on cosmic scales. Matter moves in directions that increase entropy because the structure of spacetime is trying to distribute information as evenly as possible. Gravity is not pulling objects together. Entropy is guiding them along the most probable paths. If this idea is correct, then time itself plays a central role. The reason objects move along these entropic paths is that the future contains more possible states than the present. The present contains more states than the past. Entropy rises because the number of possible configurations grows. That growth defines the arrow of time. If gravity emerges from this growth, then gravity and time are two expressions of the same principle. Gravity is the geometric manifestation of entropy increasing. Time is the experiential manifestation of entropy increasing. The holographic principle reinforces this view. According to this idea, the information that defines the volume of space can be stored on its boundary. The deeper interior of spacetime is not a separate storehouse of information, but a projection from the boundary. If information governs space, and entropy governs the organization of information, then spacetime might be nothing more than an emergent structure formed by entanglement patterns across its boundaries. In this picture, the arrow of time is not painted on the surface of spacetime. It arises from the way entanglement grows. As quantum entanglement spreads between degrees of freedom, entropy increases and spacetime geometry adjusts in response. Gravity becomes the curvature associated with shifts in entanglement. Time becomes the direction in which entanglement grows. This interpretation suggests a new way to understand the universe. Instead of starting with spacetime and inserting matter, energy, and information into it, we start with information. Patterns of entanglement define the structure of space. Changes in those patterns define the structure of time. Entropic forces arising from information gradients produce gravitational behavior. Under this lens, gravity is not a pull. It is a bookkeeping rule for information flow. It ensures that the fabric of spacetime evolves consistently as entanglement spreads. Now return to the early universe. It began in a state of astonishing low entropy smoothness. That smoothness meant very little information was encoded in the large-scale geometry of spacetime. Entanglement was relatively uniform and sparse. Gravity had very little structure to work with, but that lack of structure created a vast potential for entropy to grow. As minor fluctuations appeared, entanglement patterns began to shift. Gravity amplified these shifts. the flow of information increased, spreading through spacetime like ripples in a pond. Entropy rose. Time gained direction. The arrow of time did not emerge as an afterthought. It emerged as the dominant principle guiding the evolution of information in an expanding universe. In this light, black holes become more than exotic objects. They become the ultimate expressions of entropic geometry. Their entropy is enormous because their event horizons encode vast amounts of information. Their surfaces are not physical barriers, but informational boundaries separating one region of spacetime from another. When matter falls into a black hole, the information associated with that matter is stored on the horizon in a manner that preserves the informational structure of the universe. The black hole grows because spacetime must reorganize itself to accommodate the new information. The increase in entropy follows naturally. The arrow of time deepens as the horizon expands. This idea also provides a new way to think about Hawking radiation. A black hole evaporates extremely slowly because quantum fluctuations allow pairs of particles to form near the horizon. One particle escapes outward while the other falls inward. The escaping particle carries away energy and entropy. Over time, the black hole shrinks. Information that was once hidden behind the horizon slowly leaks into the universe. The evaporation is irreversible. It increases entropy. It shows that the arrow of time operates even in regimes where classical geometry breaks down. Quantum information continues to flow in a direction that defines the passage of time. If gravity truly emerges from entropy, then the entire history of the universe can be reinterpreted as the unfolding of information. The Big Bang was the moment when the universe began in an incredibly low entropy configuration. Entanglement patterns were minimal. The informational structure of spacetime was smooth and simple. As the universe expanded and cooled, entanglement increased. Information spread through the cosmos as matter interacted, collapsed, fused, and radiated. Stars formed, galaxies assembled, black holes grew. At every stage, entropy increased. Gravity followed. Time flowed. This perspective reframes the great question of physics. Instead of asking why gravity shapes the arrow of time, we might ask why the arrow of time shapes gravity. Why does increasing entropy generate curvature? Why does the universe respond to information flow by creating gravitational wells and expanding horizons? These questions may hold the key to a unified understanding of spacetime, quantum mechanics, and thermodynamics. They suggest that the universe is not a static arena, but a dynamic information processing system. Yet despite these bold possibilities, uncertainty remains. Entropic gravity is a compelling idea, but it is not universally accepted. Some argue that it explains certain cosmic behaviors, but not others. Some believe it captures deep aspects of reality, while others caution that it may be an approximation rather than a complete theory. What is undeniable is that the relationship between gravity, information, and entropy runs deeper than classical physics ever imagined. Each discovery reveals that the universe might be built from principles more abstract than matter and energy. This chapter leaves us with a striking possibility. Perhaps gravity is not the engine behind time's arrow. Perhaps the arrow itself is the engine behind gravity. Perhaps entropy does not simply grow in a universe governed by geometry. Perhaps geometry grows in a universe governed by entropy. If so, then the connection between gravity and time is not incidental. It is foundational. Time flows in the direction of increasing entropy because the evolution of spacetime itself demands it. Spacetime has always been described as a smooth fabric, a continuous stage upon which matter moves and events unfold. This image has guided physics for more than a century, yet deeper investigations into quantum theory suggest that spacetime may not be fundamental at all. Instead, it might be woven from threads of entanglement, a quantum property that links particles so thoroughly that they behave as parts of a single system, even when separated by great distances. If entanglement forms the scaffolding of spacetime, then the geometry we observe could be nothing more than the visible outline of an invisible network of quantum relationships. In this view, the arrow of time may arise not merely from entropy, but from the spread of entanglement itself, an expansion of information that shapes both space and time. To imagine such a universe, you must abandon the idea that space is a container. Instead, consider that space might be the consequence of how quantum systems share information. When two particles become entangled, the information describing them cannot be separated into individual pieces. It becomes a single shared description. If many particles become entangled in particular patterns, those patterns define distances, directions, and the curvature of the world they inhabit. Researchers exploring these concepts discovered that when entanglement between regions increases or decreases, the geometry of spacetime adjusts in ways that resemble gravitational behavior. Space can expand, contract, and bend depending on how entanglement is distributed. Gravity might thus be the visible geometric expression of invisible quantum linkages. This idea gained remarkable clarity when physicists studied the relationship between black holes and quantum entanglement. When a black hole forms, it seems to swallow information, hiding it beyond the event horizon. However, quantum mechanics forbids the destruction of information. The tension created by this rule led to a series of proposals that suggested black holes do not destroy information, but store it in highly entangled states. This insight led to the dramatic claim known as ER equals EPR. In simple terms, it states that entangled particles might be connected by a kind of tunnel through spacetime. These tunnels are not literal passages for travel, but geometric representations of quantum connections. Entanglement and geometry become inseparable. The universe may be held together by these quiet quantum relationships, weaving the fabric of space itself. If the fabric of spacetime emerges from entanglement, then the arrow of time may arise from the natural tendency of quantum systems to become more entangled. When two systems interact, they share information. Their states become correlated. This increase in entanglement resembles the increase in entropy. It creates more possible arrangements of information and more possible configurations of the universe. Just as entropy grows because mixed states are more probable than separated states, entanglement grows because interconnected states are more common than isolated ones. If space is born from entanglement, then the increase of entanglement literally reshapes space-time. It defines what regions are connected and how geometry evolves. Time emerges because the spread of entanglement has a direction. It moves from low entanglement in the early universe toward high entanglement in the future. Picture the Big Bang through this lens. In the beginning, the universe was smooth and simple. It contained matter and radiation in nearly uniform arrangement. The entanglement patterns were sparse and limited. As the universe expanded, particles interacted, collided, and exchanged information. Their entanglement grew. This growth defined the large-scale structure of spacetime. Gravity acted on matter, amplifying tiny fluctuations. Entanglement acted on the quantum states beneath, shaping the geometry in which gravity could operate. Both processes increased entropy. Both defined the arrow of time. The past was a place of limited entanglement. The future is a place of vast entanglement. The illusion of time's flow arises because the universe naturally evolves from simpler informational states to more complex ones. This can be seen in the behavior of black holes as well. A black hole possesses enormous entropy because of the staggering number of microscopic configurations that correspond to the same macroscopic appearance. These configurations are thought to exist in highly entangled forms among the fundamental degrees of freedom of spacetime. When matter falls into a black hole, the entanglement between the black hole and the rest of the universe increases. This increase defines the arrow of time for black hole physics. The black hole grows, its horizon expands, its entropy rises. Even the evaporation of a black hole is shaped by entanglement. Hawking radiation is entangled with the internal states of the black hole, and as the radiation escapes, it carries away information in subtle patterns. the outward flow of entangled radiation is irreversible. It is another expression of the arrow of time born from quantum behavior. These ideas also reveal a deeper point about why time only moves in one direction. Quantum entanglement is extremely difficult to undo. Once systems share information, reversing the process requires extraordinary coordination. You must disentangle states with impossible precision, reversing every interaction and every correlation. This is so unlikely that it might as well be forbidden. In everyday life, entanglement spreads continuously and irreversibly. Even the simplest actions, such as light striking your eyes or air molecules colliding with your skin, increase entanglement between you and the world. The growth of entanglement is the quantum foundation of macroscopic irreversibility. It is the microcosmic story that entropy tells on a larger scale. Entanglement expands, information disperses, the arrow of time grows sharper. If space-time depends on entanglement, then the universe itself expands, not only because space stretches, but because quantum correlations extend across greater regions. As matter separates into galaxies, these structures remain connected through ancient entanglement established in the early universe. Gravity shapes their motions, but the geometry in which gravity operates may be written in the language of entropy and entanglement. Paths that objects follow may arise from how space-time tries to maintain consistent informational structure while entanglement spreads. Gravity may not be a pull. It may be the result of space-time adjusting to informational changes. This perspective also offers a new interpretation of cosmic evolution. As the universe ages, entanglement grows. Regions that were once separate become correlated through their shared histories. Particles that have never interacted directly become entangled through indirect processes. Radiation travels across the cosmos, spreading information and increasing the complexity of global entanglement patterns. The geometry of space-time reflects these patterns. It curves in response to energy and mass because those quantities influence how information is distributed. In this framework, the arrow of time is the arrow of entanglement. The direction of entanglement growth is the direction in which space-time evolves. If this is true, then time itself is a measure of how much entanglement has accumulated. The past was a state of minimal entanglement. The future is a state of maximal entanglement. This interpretation resolves the mystery of why we cannot remember the future. The future is not yet entangled with the present. Memory is a physical record encoded in entangled states between your brain and the environment. These states exist only after events occur. They cannot be established in reverse. This insight exposes a profound connection between consciousness and the arrow of time. Your awareness moves forward because your brain continuously entangles new information. Every perception creates correlations between neurons and the world. These correlations cannot be removed. They embed the present into physical systems in a way that defines before and after. The arrow of time is thus not solely a cosmic phenomenon. It is also a biological and informational one. The universe and the mind both follow the same direction because both are governed by the irreversible spread of information. With these concepts in view, the universe becomes a place where gravity, entropy, space-time, entanglement, and time are interwoven. None stands alone. Each emerges from the others. The arrow of time may not be a rule imposed upon the universe. It may be the unfolding of the universe's informational structure, a story written through the expansion of quantum relationships. Space expands as entanglement expands. Time advances as entropy advances. Gravity curves the stage as information flows across its surface. This brings us to a philosophical turn. If space-time emerges from information, and if the arrow of time emerges from entanglement, then what came first? Did gravity give birth to the arrow of time by amplifying cosmic imperfections? Or did the arrow of time, written by entanglement and entropy, give birth to gravity? Are space-time and time's direction co-emergent, produced simultaneously by the deep rules that govern information? These questions lie at the frontier of physics. They challenge the assumption that the universe is built from matter and ask instead whether it is built from relationships. In the next chapter, we face the great debate directly. Does gravity create entropy, or does entropy create gravity? Does the arrow of time emerge from space-time curvature, or does curvature emerge from the arrow? The universe may not choose one answer. It may reveal that both views are true in different ways, bound together by the low entropy beginning from which everything unfolded. The universe presents us with two grand narratives for explaining why time has a direction. One tells us that gravity sculpts complexity from the smoothness of the early cosmos, amplifying tiny imperfections into stars, galaxies, and black holes, each step increasing entropy and sharpening the arrow of time. The other narrative suggests that the arrow of time is more fundamental than gravity, that the rise of entropy creates the very curvature of space-time and gives birth to the force we call gravity. These narratives seem to compete, yet both are supported by compelling evidence. They weave around each other like two threads of the same fabric, raising the question of which story came first, or whether the distinction even makes sense. To understand this tension, imagine the earliest universe as a pristine and simple state, so uniform that it contained hardly any structure at all. This smoothness represented astonishingly low entropy from the perspective of gravity. There were only a few possible configurations that could match such perfect balance. As the universe expanded, gravity seized upon tiny fluctuations and amplified them. By doing so, gravity increased entropy and created the great cosmic structures we see today. Under this view, gravity appears to be the engine of time's direction. It is the force that turns simplicity into complexity. In this interpretation, the arrow of time emerges because gravity pushes the universe towards states of higher entropy. But there is another interpretation that looks deeper. It suggests that gravity may not be fundamental. Instead, gravity might emerge from the statistical behavior of microscopic degrees of freedom that carry information and become entangled over time. Under this interpretation, entropy does not merely follow gravity. It creates the conditions that give rise to gravity. Gravity becomes a geometric expression of how information is organized in the universe. If this is true, then the arrow of time, defined by increasing entropy, may be the primary driver of cosmic evolution. Gravity would exist because the universe is moving from a state of low entropy toward one of high entropy, adjusting its geometry to accommodate the spread of information. Both interpretations hold pieces of truth. The observable universe tells us that the early conditions were spectacularly smooth, giving gravity room to increase entropy. The quantum view tells us that entanglement grows irreversibly, and this growth may shape space-time itself. The puzzle is whether one of these descriptions should be considered more fundamental, or whether the universe requires both to form a consistent whole. Let us explore the first view more deeply. In this classical perspective, gravity dominates the early universe by amplifying microscopic fluctuations into macroscopic structure. A region slightly denser than its surroundings attracts more matter. Over time, it grows denser, forming clouds, then stars, then galaxies. With every collapse, gravitational energy is converted into heat. Heat spreads into the environment. Entropy increases. This kind of irreversible evolution is what gives time its arrow. It proceeds from the simple toward the complex. Gravity appears to create the arrow by turning the universe away from its improbable beginning towards states that are far more probable. If the universe had been born in a high entropy state, time would lack direction. It might unfold without complexity, or perhaps not unfold at all. Yet this view does not explain why the early universe began in such a low entropy state. Why did gravitational entropy start near its minimum? Why was matter spread so uniformly? If gravity creates the arrow of time by amplifying small differences, what created the initial conditions that gravity needed in order to operate? The puzzle of the beginning remains unaddressed. Gravity is powerful, but it cannot explain the origin of its own stage. The second interpretation tries to provide that missing explanation. In this view, entropy and information are the true foundations of the universe. They govern the structure of spacetime and determine how matter moves. As entanglement spreads, spacetime geometry adjusts, producing the behavior we describe as gravitational attraction. Time flows forward because entanglement and entropy increase. Space curves because information changes. The arrow of time becomes the engine of evolution, and gravity becomes a function of that evolution rather than its cause. One of the central insights supporting this interpretation comes from black hole thermodynamics. Black holes have entropy proportional to the area of their event horizons. This fact suggests that information about the interior of a black hole is stored on its surface. The holographic principle extends this idea, claiming that the information content of any region of space is encoded on its boundary. If this is true, then spacetime geometry is a large-scale effect of underlying informational structures. Entropy governs how these structures evolve. The arrow of time emerges from this increase in entropy, and geometry bends accordingly. If so, then gravity is a thermodynamic consequence rather than a fundamental force. Consider what this means for cosmic history. The early universe began smooth because the information content on the cosmic boundary was simple. Entanglement was minimal. As the universe expanded, interactions increased entanglement, creating new informational structure. This process defined the evolution of spacetime. Gravity emerged as the geometry needed to maintain consistency between entanglement patterns and energy distributions. In this way, the arrow of time created the conditions that gave rise to gravity. Gravity was not shaping entropy. Entropy was shaping gravity. Despite the power of this interpretation, it does not fully replace the classical view. Gravity undeniably shapes the formation of stars and galaxies. It dictates the structure of the cosmic web. It guides the motion of planets and the collapse of black holes. These effects are real and measurable. Even if gravity emerges from deeper principles, its role in amplifying complexity and driving entropy remains essential. The arrow of time becomes visible through gravitational processes. Without gravity, the universe would gain little structure. Even if the arrow existed in principle, it would be nearly invisible in practice. So which came first, gravity or the arrow of time? The universe may not allow such a simple answer. Both appear to originate from the low entropy beginning. Both reflect the same underlying asymmetry. Entropy was low at the start, and gravity amplified it. Entanglement was sparse at the start, and its growth gave rise to geometry. The arrow of time may not be caused by gravity, and gravity may not be caused solely by entropy. Instead, both may emerge from the same fundamental boundary condition, the astonishing smoothness of the early universe. This boundary condition may be the true origin of the arrow of time. All laws of physics, except the second law of thermodynamics, are time-symmetric. They do not prefer one direction. But the universe did not begin in an average state. It began in an extraordinarily special one. The low entropy initial condition gave the universe room to evolve. It created the gradient that both gravity and entropy follow. Time's direction may be nothing more than a consequence of this boundary condition. From this perspective, the great debate resolves into a single idea. Gravity and entropy are not independent forces competing to define time. They are expressions of a deeper asymmetry coded into the universe from the beginning. Gravity amplifies the asymmetry by creating structure. Entropy measures it by tracking how far the universe has drifted from its simple origin. The arrow of time is not imposed by any one law. It is the story of the universe unfolding from its improbable start. As the universe grows older, gravity continues to shape structure, entropy continues to rise, and entanglement continues to spread. The arrow of time remains sharp because the universe has not yet exhausted its potential for complexity. Long into the future, when stars fade and black holes evaporate, entropy will reach its maximum. When that moment arrives, the arrow of time may blur. With no more gradients to follow, the universe may enter an era where nothing changes in a meaningful way. Time will still exist as a coordinate, but not as an experience. The arrow will fade because the asymmetry that once guided it will vanish. Before we reach that distant conclusion, we must take one more step in our journey. If gravity and entropy both trace their origin to the same boundary condition, then what does this mean for the universe as a whole? What does it mean for the nature of time? The next chapter offers a final synthesis, bringing together gravity, entropy, entanglement, and the remarkable simplicity from which everything arose. The universe began in a moment of astonishing simplicity, a moment so smooth and so low in entropy that it stands as one of the greatest mysteries in all of physics. Everything that followed, every star that burned, every galaxy that spiraled, every molecule that formed, every breath ever taken, and every thought ever conceived has unfolded from that initial perfection. The entire story of time's direction is contained within that beginning. To understand why time flows forward, why the past is fixed and the future open, why entropy rises, and why gravity sculpts complexity, we must return to that first instant and examine the extraordinary conditions from which the cosmos emerged. Imagine the earliest universe as a vast and glowing field, uniform in temperature and density, without clumps, storms, or structures. This smoothness was more than a visual state. It was a physical one, representing an exceptionally low gravitational entropy. Gravity prefers disorder. It prefers collapsed structures, dense regions, stars, black holes, and cosmic webs. A universe filled with such structures possesses a staggering number of possible configurations. But the infant universe had almost none of these. Its smoothness meant that it occupied one of the rarest possible states. It sat at the very bottom of a cosmic valley of improbability. From this valley, the only direction to move was upward toward higher entropy, toward complexity, toward a future filled with change. Time's arrow was encoded in that simplicity. It did not need to be written into the laws of physics. It emerged naturally from the initial conditions. Everything that followed was a consequence of the universe climbing away from its low entropy past. As the cosmos expanded, tiny fluctuations grew. Gravity amplified them relentlessly, pulling matter inward, creating clouds that collapsed into stars, and stars that collapsed into black holes. Entropy surged. With each surge, the arrow of time strengthened. The universe moved from uniformity to complexity because complexity was overwhelmingly more probable. In this sense, gravity acted as the great amplifier. It took the small imperfections of the early universe and magnified them into the vast structures we see today. But gravity was not the source of the arrow. The arrow existed because the universe began in a state with enormous potential for change. Gravity simply unlocked that potential. It converted potential energy into heat, motion, and radiation, all of which increased entropy. Every star that formed, every explosion that tore through interstellar space, every merger between galaxies, and every black hole that grew represented the universe drifting further from its simple past. Gravity did not create irreversibility. It revealed irreversibility. At the same time, entropy shaped gravity. Quantum theories of spacetime suggest that the geometry of the universe may arise from the distribution of information, from the patterns of entanglement between quantum systems. In this view, spacetime is not fundamental. It is an emergent structure built from relationships. The The curvature of space may be a reflection of how information is stored, shared, and reshaped. Gravity then becomes a macroscopic shadow cast by microscopic processes. It emerges from the tendency of systems to maximize entropy, to spread information, to follow the direction most consistent with probabilistic evolution. If this perspective is correct, the arrow of time is more fundamental than gravity. It is the increase of entropy that shapes geometry, not the reverse. Time flows forward because the universe naturally evolves toward more probable states. Spacetime adjusts to these changes, bending as matter moves and responding to the spread of information. Gravity is one of the ways the universe expresses its informational dynamics. The arrow of time is another. Both perspectives converge on a single truth. The arrow of time and the force of gravity are inseparable because both are consequences of the same initial asymmetry. The early universe was too perfect. Its smoothness created a vast gap between what existed and what could exist. That gap was the fuel for cosmic evolution. Gravity transformed the gap into structure. Entropy transformed structure into history. Time flowed because the universe had room to change. Without the low entropy beginning, time would have had no direction. Consider the everyday world through this lens. The heat of a fire, the glow of a star, the mixing of air, the aging of living creatures, the crumbling of mountains, and the slow drift of continents are all consequences of entropy rising as the universe moves away from its improbable origin. Each event records the passage of time because each event increases the disorder of the world. You feel time, not because your mind creates an illusion of flow, but because your body and brain are entangled with countless irreversible processes. Your memories form because entropy increases. Your thoughts proceed because your neural circuits consume energy. Consciousness is part of the arrow of time because it depends on the flow of information and the dissipation of energy. This reveals a startling unity: the fall of a star into a black hole, the fusion of atoms in stellar cores, the quiet decay of radioactive elements, and the flicker of awareness in a human mind are all expressions of the same principle. They all move in one direction because they all rely on the universe's irreversible drift toward higher entropy. The arrow of time is not a feature of cosmology alone. It is the foundation of experience. It is written into the universe and reflected in the mind. As the universe continues to expand, entropy will keep rising. Black holes will swallow matter and grow. Stellar processes will run their course. Eventually, even black holes will evaporate through the slow emission of Hawking radiation, releasing faint bursts of energy into an increasingly cold and empty cosmos. In the far future, after unimaginable spans of time, the universe will approach equilibrium. Entropy will reach its maximum. When that moment comes, the arrow of time may fade. There will be no more gradients to follow, no more structures to collapse, no more stars to burn, no more information to reorganize. Time will not end, but it will lose direction. Every moment will resemble every other. The universe will become a quiet sea of uniformity once more. In this distant era, the simplicity of the beginning will echo in the simplicity of the end. The universe will have completed its journey from low entropy to high entropy. The arrow of time, born from the improbable smoothness of the early cosmos, will have served its purpose. The drama of structure, heat, evolution, and thought will cease. But the memory of the arrow will remain etched in the cosmic history that preceded the stillness. This brings us back to the great synthesis. Gravity sculpted the universe. Entropy drove it forward. Time found its direction in the difference between the beginning and the end. Everything that exists is part of that great unfolding. The arrow of time was not imposed upon the universe. It emerged from within it, shaped by the very conditions that brought the cosmos into being. The universe began in a breath of perfection. Gravity stirred that perfection into motion. Entropy guided the motion into complexity. Time flowed because the cosmos could not remain still, and across billions of years that flow carried matter, energy, and information into forms capable of reflecting upon their own origins. Gravity sculpts the universe. Entropy drives it forward. Together, they give time its direction, a direction written in the universe's first moment.